Hello everyone, and thanks for clicking this tutorial video. In this tutorial, we're going to cover from the very basic of finite element methods to the hierarchical deep learning neural network. We call it hidden and convolution hidden. I'm Chanwook Park, a fourth-year PhD student working with Prof. Kam Liu at Northwestern University. Here's the outline. We'll first start with the very basic undergrad level derivation of the 1D linear elasticity equation. Then we'll introduce the final method and hierarchical deep learning neural network, we call it hidden, then convolution hidden for C-HiDeNN. At the end of each tutorial, I'm going to introduce the programming part with the Python, the Jupyter notebook on each example. All right, and let's get started. So let's start from the very basic. I think most of you already knows about this. So if you are very familiar with this, please skip this part. Directly go to finite element or hidden lectures. But let's start from the very basic. So consider a segment of delta x of a 1D deformable beam. So we're going to solve a 1D problem, linear elasticity problem, where there is a uniform cross-section area of A. So here's a delta x, and the force is defined as Fx. So there's a force acting on the left side and right hand side. And when there's a force F is acting on this delta x, we can define a stress field as a force divided by area. You can view this as a pressure acting on the surface. And there's also another type of force which is called the body force. You can think it as a gravity acting on the body. So from the Newton's second law, where the law is density and A is acceleration, we can do the summation of the forces along the x-axis, right? And you can rearrange this and divide by the cross-section area A. Now you have this equation. And if you have delta x to the 0, then you'll have this differential equations. Now this differential equation is a first order differential equation for the stress field sigma x. But actually we want to find out the displacement field instead of stress. So we want to link between the stress field into the displacement field. But before we go there, we want to add more assumption. For simplicity, there's no acceleration, so it's not a time-dependent problem. So we drop the acceleration term here. Now this is a static equation of motion, right? And I want to link the stress field with the displacement field through the Hooke's law. So this is a Hooke's law. Basically, the sigma is a product of a constant called Young's modulus times the derivative of the displacement field, which is called the strain. So basically it's the strain times elastic modulus. So if you plug this in, then our governing equation, which is called strong form, becomes this. All right, it's a second order differentiable with respect to u, the displacement field. And also there's a boundary condition. It depends on the problem. Right. So this is the problem statement that we want to deal with. There's a body force of 1 across the entire body, and there's no force acting on the right end, and it's a fixed on the left end. So this is our strong form with the boundary conditions. So since it's a 1D problem, the solution of our PDE, which is our displacement field, is also a function, 1D function defined at the boundary of 1n, 0n, L. And as the function has two ends at x equals 0 and x equals L, we need two boundary conditions to solve this PDE. So like I said before, on the left-hand side, it's going to be 0 displacement. And on the right-hand side, it's going to be a stress field of F. Remember here, because it's a force, you're going to convert u, that is displacement, into a strain, and times Young's modulus becomes stress. And if you product with area, it's going to be a force. So now it is your force boundary condition on the right end. Next, for this tutorial, there's actually the reason that I choose this problem, because we can actually solve this with hand. There's an exact solution. So let's go step by step. It's very simple, as easy math. So since our second order derivative of u is -1, we can do the integration twice with these two integral coefficients. And when we apply the boundary conditions on each end, you will be able to find the exact values of these coefficients, C1 and C2. Now this is our exact solution, which is a second order polynomial. This is a smooth field that we want to find out. All right, that's it for this tutorial, and I hope you see you in the next tutorial. Thank you.